Hi everyone, my name is Manlo. Today I'm gonna present our work, the data-driven demand prediction for fast expanding electric vehicle sharing systems. As we all know, the mobility is the lifeblood of modern cities, and recently it is often said that the mobility solution for future smart cities should be electric and shared, because it offers clean, reliable, and affordable ways to get from location A to B and back again. It has been increasingly popular all over the world, from London to Singapore, Shanghai, and attracts lots of interests from government, industry, and academia. So how do they work in practice? Basically, it contains a number of stations with charging facilities scattered around the urban space, and users can pick up vehicles from them, drive around, and return to the same or any other stations. And then they plug in the vehicles for charging and pay based on the rental time, so a transaction has been completed. As in other urban systems, for shared e-mobility, a key problem is how to predict the mobility demand across space and time. It is an essential ability to answer many what-if questions. For instance, if a new station were to be deployed to a particular location at a specific time, how popular it will be, and how an existing station will perform at a future time. This may be straightforward if the system is static, but in practice, the mobility system can be highly dynamic. For instance, the shared e-mobility system we worked with was continuously expanding at an impressive speed, having 2 times more stations and 4 times more vehicles within 12 months. And we can see that the system also expanded to new areas without previous coverage. So we need to embrace such dynamics and make predictions for locations with limited or no historical data. In addition, we also observe that the impact of such dynamics is often non-trivial, which makes prediction even more challenging. For example, we see that the same event of deploying a new station may have opposite effects. On the left, this new station steals demand from the existing ones because it was deployed in a large shopping center, so everyone tends to use it. On the other hand, this new station boosts the demand of its neighbors, since it was deployed at the other terminal of the airport, which creates lots of short transits. This means we need to design an approach that can capture all those complex dynamics in spatial temporal domain. To do that, we use 2 layers of encoders, where the first layer, in the form of LSTMs, captures local temporal dependencies, for example, the historical mobility at particular points and weather history. And on top of that, we use a graph convolutional neural network to encode spatial correlations from various data modalities, such as a point of interest and a raw network. And our model can also do multi-scale prediction, in that it can predict both long-term expected demand and short-term instant demand over spatial temporal domain by plugging different final layers to the network. We evaluate our approach with data collected in Shanghai over 1 year, which has roughly 4,000 charging stations, 16,000 vehicles, 0.4 million users, and 7 million recalls. We also use road network data, point of interest data, and weather records in Shanghai. Results have shown that our approach could achieve much better prediction performance, up to 3 times gain over state-of-the-art. More importantly, it is also more resilient to perturbations induced by different layers of dynamics. For example, how fast the events of deploying or closing stations happen, as shown in the right figures. Many thanks for listening.